Tommy with us, and he's going to tell us about the flow-preserving ZX calculus rewrite rules for optimization and obfuscation. Thank you.
Thanks. Hi everyone. So I gave a talk on this paper at QPL last year, and so many of you will have seen that. And so I decided to try and make this talk more about giving more intuition for flows and kind of giving it from a kind of ground up perspective. As previous talks, I've had to show the definition of Pauli flow, and it immediately switches everyone's brain off. So first, MBQC involves us. We basically we prepare a load of states and a load of qubits in the plus state, entangle them together with CZ gates, and then we perform some measurements. So we can entangle a load of stuff together like this, choose what we want to measure them in, and this is how we perform our computation. So here we've chosen all of them apart from alpha 4 to be XY measurements, and alpha 4 is a YZ measurement. This was just some random choice just to show you what it could be. So for the kind of definition-y side, we have graph states and we have MBQC form diagrams. So a graph state is just a load of qubits that are prepared in the plus state and entangled together. And all of the qubits have outputs coming from them. And then an MBQC form diagram is where we allow some of these outputs to kind of be composed with caps or with measurement effects, so that we end up with all output vertices have no measurements, all non-output vertices have measurements, like so. And we still have everything is green spider entangled together with CZ gates. Importantly, we can measure in 3 planes or the 3 Pauli angles. XY measured vertices are just green spiders. YZ measured vertices are red spiders, and XZs have this red alpha with a pi/2 in front of it. These will be useful later, but mainly we'll be talking about XY measured vertices for intuition. So we're going to be talking about corrections in MBQC, and we're going to start with the most basic one. So say we have this first diagram where we've measured A at an angle alpha, but we've got some error. Using simple ZX rules, we can detach the pi from the alpha, push the pi onto the leg, push it through the Hadamard gate so it becomes red, and then either pi copy or use the identity rule on B so that we now have a red pi on the output. So now we know, because of this, if there was an error on A, we could simply add a red pi to the output to undo the error on A. Also, any local Cliffords on outputs can be classically post-processed for. But yeah, if we can always push an error onto future qubits, then our diagram's correctable and deterministic. So for a slightly more complex example, although this is barely more complicated, consider the following diagram. So now we say, again, let's say we get an error on A. We can push the error to become a red pi on C's output, but we also will obtain a green pi error on B here because C is connected to B. And therefore, we need A to be measured after B if we want to do it like this, because we get both the error on C and the error on B. So here we need to measure the qubits A first, then B, and then C and D afterwards. So what can we say from this? So for a diagram with only XY measurements to be correctable, we need to be able to, for every measured vertex V, be able to push its error onto one of its neighbors. That is, say, C here, which gets the red pi. And we need V to be measured before all of the corrected vertices other neighbors. So for the same example, C is what we're calling A's corrector, and then all of the vertices that get green pies as well, which are all of C's other neighbors, also need to come in the future of A. So this is actually just the definition of causal flow. Causal flow is just all of the diagrams which are correctable by pushing a phase onto its one nearest neighbor, or pushing an error pi onto one nearest neighbor. So beyond this, some diagrams, causal flow isn't enough. So this is the standard diagram for something that has gflow but not causal flow. And this doesn't have causal flow because all of the outputs have two or more neighbors. So whichever one of A, B, and C you try and correct last is going to have some after effect on one of its neighbors. And so we're not able to do this with causal flow. So for example, say we corrected A on D, B on E, and then we're trying to correct C on F. Well, we get some error on C, we push it through to F, but we also get pi's on B and A, which, because we said we're doing A and B before C, this isn't wanted. However, if we allow ourselves to push the pi phases forward multiple times, we see we could push the green pi on B onto D, and the green pi on A onto D, like follows. And now we end up with just a red pi on D and a red pi on F, which is completely allowed. And so if we allow multiple vertices to appear in the correction set, or multiple vertices to obtain red pi's, then we can kind of get more than we did with causal flow. So this can be thought of as, allowing correction sets to have more than one vertex, or allowing ourselves to push pi's into the future more than once. So from this, it's not always obvious how many pi's you'll need to push forward and where they'll end up. And so we get something which helps us a bit more with this, called the fixed point property. So the fixed point property can be just thought of as inserting two red pi's, which is essentially the identity, on some spiders. And then if we push one set of the red pi's through the adjacent spider, we'll get green pi's on all of the spiders that have an odd number of neighbors in D, as seen. And we can use this to find correction sets quite easily. So for example, this second vertex from the top has a green pi on it. And say we got a green error on the second vertex from the top. Well, then we know that if we put a red and a green pi on the third vertex, a red pi on the fourth vertex, a red and a green on the fifth, a red on the sixth, and a green on the seventh, that we're just implementing some stabilizer here. And so we obtain the same diagram. And so to undo a green pi error on the second qubit, all we need to do is add these other errors to the future qubits, and this can undo for the error on the green pi. And this is kind of almost enough to define extended gflow already. So with extended gflow, so when we have extended gflow, we have multiple measurement planes. And if we notice from the fixed point theorem, anything in the correction set gets a red pi, and anything in the odd neighborhood of the correction set gets a green pi. So here, D is the correction set, and all of these ones that get green pi's are the odd neighborhood of the correction set. So if we wanted to move to multiple measurement planes, we said YZ measured vertices were red alphas. And so an error on a YZ measured vertex would just be a red pi, sorry. And an error on a XZ measured vertex would be a red pi and a green pi. So the fixed point theorem tells us that to correct a YZ measured vertex, it needs to be in its correction set and not its odd neighborhood, so it just gets a red pi. To correct a XZ measured vertex, it needs to get a red pi and a green pi, and so it needs to be in both its correction set and its odd neighborhood. And as before, XY measurements just get a green pi error, and so they need to be in the odd neighborhood when using the fixed point property. So now we can essentially define extended gflow. So extended gflow, we just need that for every vertex v that is measured, it comes before all of the other vertex that get green or red pies when correcting for an error on v, and v must get the correct correction depending on its measurement plane. That is, like I said, obtaining a green pie if it's xy, obtaining a red pie if it's yz, or both if it's xz. So that's essentially the entire definition of extended gflow, but just kind of simplified down a bit. And we could also quite easily talk about Pauli flow from this. So Pauli measurements, when we apply certain corrections, are unchanged. So if we apply a Pauli X gate to a Pauli Z measurement, sorry, Pauli X measurement, it does nothing. If we apply a Pauli Z gate to a Pauli Z measurement, it does nothing. And if we apply both to a Y measurement, it does nothing. And what this means is we can allow Pauli measurements to get certain to be in certain correction sets or odd neighborhoods dependent of future vertices. So, for example, a Pauli X measurement can be in the correction set of any future measured vertex because the correction does nothing to the Pauli measurement. So if we just combine the condition that we allow certain Pauli measurements to appear in future correction sets with our definition for extended gflow, we have all of Pauli flow. So yeah, this is, I think, fairly intuitive way of looking at it. This is all of the long 9 condition definition says. It just says it has two conditions talk about the order. No, yeah, I believe 3 conditions talk about the order, and then 6 talking about the different measurement planes. But essentially all it says is V comes before all vertices apart from Pauli vertices that obtain red or green pies, and each measured vertex needs to get the right correction. And that's all of Pauli flow. So now on to rules that preserve Pauli flow. So this is what the majority of mine and Miriam's research has been on. So first we have some rules which were proven by other people to preserve Pauli flow and G-flow. So these are the local complementation rule and the pivoting rule. These are used a lot throughout many different areas of ZX research and just quantum computing research in general. And it's I'm not going to go into too much detail with these here. Similarly, Will Simmons in his 2021 paper proved that we can delete any Z-measured qubit and that this preserves the existence of Pauli flow. I don't know why I've cited myself here. I thought I'd got rid of that, but we proved in 2022 that we can arbitrarily delete Z-measured vertices and preserve the existence of Pauli flow. And the idea with this is that Z-measured vertices just need to appear in their own correction sets. And so we can just, this Z-measured vertex appears in its own correction set. If it gets an error, we just put green pies on all of the neighboring vertices. So this is the kind of first key work done in our paper. And so in the graph-like diagrams used in physics, we represent all diagrams as only green spiders. And so a phase gadget consists of a green spider connected by a Hadamard wire to some alpha. This is slightly different to the MBQC form diagrams we do, where we want all vertices to have a measurement effect, all non-output vertices to have a measurement effect that they're connected to with a plane wire. And so there's kind of 2 choices of what we can do with this. We can either you apply the Hadamard on this wire to the alpha to get a red alpha, which is a YZ measured vertex, as seen on the left at the bottom. Or we can consider the vertex on the left here to be a XY measured vertex, an X measured vertex, and the measurement on the right to be a XY measured vertex, and we obtain the diagram on the right where we have two qubits here. And it's somewhat unclear which of these two interpretations of a phase gadget is correct, or what should we use when we're dealing with MBQC and Ford diagrams. And we've actually proved that either of them is fine, either of them works, and they're completely interchangeable. So using the rules we've already mentioned, we can insert this Z measured qubit X prime at the bottom without changing the interpretation of the diagram and while preserving Pauli flow. And then we can apply a pivot on the edge between X and X prime, which gives us the diagram on the right, which is exactly the diagram we had on the right on the slide before. So we can actually do this with XZ measurements as well. So we can insert a X measured, a Z measured qubit. We can pivot. No, we can do a local complementation, sorry, on X to get rid of the pi over 2 phase. And then we finally oh no. Yeah, that's exactly what we've done. And we do a local complementation on X. This puts a red pi by 2 on X prime. And then we can do a pivot again. And so we've found ways to get rid of both XZ and YZ measured vertices. And so we've developed a procedure for getting rid of all other planar measurements and leaving us with just X, Y, X, and Y measurements. So first we delete all Pauli Zs. We convert all YZ measurements into an X and an XY using the phase gadget rule. And we convert all XZ measurements into a Y and an XY using the previous rule. And we found a way to get rid of all XZ and YZ measurements. So this is nice for several reasons. It's useful in proofs as we can prove this thing is also undoable. So we only have to reason about X, Y, X, and Y measured vertices. Similarly, it's just nice for us to deal with in the same way that physics is nice because it only has green spiders. We've now found a way to do MBQC form diagrams with only green spiders. And so it's nice just from being able to do away with red's motivation. Now, on to some other rules. So this was talked about by Xushang last week and used in his paper on blind measurement-based quantum computation. And the idea is we spent a long time proving that this preserved Pauli flow kind of from the base. So given some diagram with Pauli flow on the left diagram, constructing some Pauli flow for the right diagram, and it was pages long of proofs. And then after we came up with the Z insertion rule, we realized it's just trivial. And so what we can do is if we insert two Z measured qubits as done here, and then we pivot along said Z measured qubits, and we obtain the right hand diagram. And yeah, this was used by Xushang to kind of hide the the connectivity of qubits by sending certain qubits to one server and certain qubits to another server, and so that their entanglement isn't completely obvious. And now we have the most kind of important rule we came up with, and it's the first flow preserving rewrite rule, which allows us to change phases arbitrarily. Which and more specifically, all other rewrite rules just change phases by integer multiples of pi by 2, while this allows us to split off any phase. And so there's kind of some hope this could possibly be used for Like how we got a completeness result for MBQC form diagrams in a stabilizer sense, this may be useful for some kind of completeness result for a more general fragment of computation. But the idea is, given some vertex, we can split off any of its neighbors and any of its phase onto another vertex A primed, and that this preserves Pauli flow. So the idea with this preserving Pauli flow is that as A is XY measured, it must have an odd number of neighbors in its correction set. And then so the kind of key depth of the proof comes from the fact that W is arbitrary, and so it could contain an odd number of members of A's correction set, or it could contain an even number, and so we have to define the flows differently based on whether W has an even or odd number of neighbors in its correction set, in A's correction set. And then essentially, if we split off an odd number of neighbors, then A would no longer have an odd number of neighbors in its correction set, and so we have to add X into its correction set so that it is correctable. And similarly, yeah, if W has an odd number of neighbors of A's correction set, we can just make A's correction set and A prime's correction set equal to A's correction set, and so it now has an odd number of neighbors as desired. And then the key reason this preserves Pauli flow and not G flow is that sometimes we can end up in a situation where X is in A's correction set, but A is also in X's correction set. This is one of the cases that's required, and essentially because X is Pauli measured, we can have X in A prime's correction set and A prime in X's correction set without this violating the rules. Whereas in G-flow, we're not allowed to have two neighboring vertices be in each other's correction sets, as this would mean both of them precede each other, and then we get a kind of error there. So we got many rules from this splitting a vertex rule. So first, if we just split off a vertex where W is empty and this phase is 0, we get this other rule, which was used by Xushang. And I think it's essentially he used it so you can kind of trick a server into thinking you have extra connections which aren't actually useful. But yeah, I'm not sure exactly how he used this. So I remember reading it. And more importantly, we've got the neighbour unfusion rule, which Corbini and Staudacher introduced at QPL 2022. And this is where we do vertex splitting with W is size 1. And then we can obtain this rule where alpha primed and alpha prime prime add up to give alpha, and we have this X measured vertex in between them. So yeah, this is an immediate corollary of our vertex splitting rule that this preserves Pauli flow. But in Corbinian's paper, they were focused on G flow. So we've had many conversations about this, and it turned out actually just switching to using Pauli flow was not useful for them. Originally, I'd thought if they just cared about Pauli flow and tracked Pauli flow instead of using G flow, that would give them a speed up on their algorithm, but this didn't seem to be the case. I believe the Pauli flow extraction procedure, the circuit extraction procedure kind of undid a lot of the optimization that they'd got, whereas the G-flow procedure didn't do that. And so it became an interesting question of when does this preserve G-flow? So in their paper, they claimed that neighbor unfusion preserved G-flow when the two qubits are extracted onto the same qubit. And while this is kind of nice heuristic, it doesn't really it's not a very solid thing. It's not very easy to tell when two qubits are extracted onto the same qubit, and it's not even immediately obvious what that means. And so we try to kind of give a more solid characterization of this. And so this leads on to some new work done. I've just realized I'm a bit quicker than I thought I'd been. So at QPL 2023, we introduced a sufficient condition and a necessary condition for neighbour of unfusion to preserve gflow. But we couldn't find a condition that was both sufficient and necessary. Since then, I have come up with the correct condition that's both sufficient and necessary. And it's that there is no vertex that is measured between A and B. And so it was very kind of finicky on what exactly the right condition should be, but this ended up being it. And I'll talk about a few things quickly. So the sufficiency proof is not so interesting. It's essentially, we can, given some diagram of this form where there is no V coming between A and B, we can construct a Pauli flow for the post rewrite diagram. So the diagram at the bottom right here. So yeah, the sufficiency one is not quite so interesting, but the necessity is somewhat. So for the necessity proof, if we start with the post rewrite diagram, so what we know is I haven't talked about focused flows here. I realized I've not introduced that, but a focused flow is a specific type of gflow or Pauli flow, and it has some extra properties that are quite useful to us, and especially here. So if we have this diagram, and we can just assume it's all XY measurements, or in the case where it's not all XY measurements, we can just delete them all. If we have a focus G-flow, what we know is that all focus G-flows are reversible. And so what this means is if we can run this whole diagram one way, we must be able to run it the other way. And so one kind of corollary of this is that all two arity vertices must have one neighbor which is in their correction set, and it must be in the correction set of their other neighbor, so that when we reverse the diagram, we still have each vertex is in its odd neighborhood of its own correction set. And so for this diagram to be reversible, we know that X has to be in the correction set of A primed and have A in its own correction set, or the other way around. And so what this means is we can construct a G-flow for this. If there is a focused G-flow for this, it must have X is in G of A primed is in G of X, and B is in G of A primed, or the complete other way around. We can just assume that it goes from left to right without loss of generality. And so we know that X is in G of A primed is in G of X, and B is in G of A primed. And then knowing this, we can quite easily construct a Pauli flow a G flow for the pre-rewrite diagram, where because we know that we essentially know that A directly precedes X, and X directly precedes A primed, and A primed directly precedes B, and there's no other vertices kind of coming between any of those measurements. We can construct a Pauli flow for this diagram where there's no V that comes between A and B. So that's for the necessity proof, and then the sufficiency proof is just a very kind of complicated Pauli assignment of a flow, knowing that there's no V coming between them. We can always construct a flow for this. So that's actually all I've prepared. I've expected I'd be spending more time talking about the Pauli flows and such, but it turned out I zoomed through it. So does anyone have any questions in particular? Thank you for the claps.
Thanks for the talk. I think I understand it better now.
Glad to hear. Yeah, the definitions are quite messy. I know Alex, when Alex visited, also had a quite nice definition that was slightly different, where you can kind of define Pauli flow in 3 conditions or so. Yeah, there's a lot of kind of different ways of thinking about it. I like the idea of kind of just pushing the pies around the diagram and seeing where we can push the pies into the future, because I don't think that's not really been explored all that much or talked about in the literature. Obviously, it's not as useful as like the fixed point property, which is kind of a immediately obvious way of how to do all of the corrections. But I think from a kind of intuitive point of view, it's quite nice to just go, okay, if we kind of make some timeline of this is the order in which we want to measure the qubits, when can we push the pi errors into the future to correct for things?
So may I ask, when you decide which direction that you push the pi spider, how do you make such decision? Like what determine the direction or like the procedure that you propagate the Paulis? But like not pi over 2.
Sure. So I guess it mainly is you kind of will have some predetermined notion of where you I guess as long as you construct some kind of order in which you want the qubits to be measured. So like here I said, well, the idea is you can always push the pies around as much as you want. So I could push this pi on the A onto the D and leave the pi from the B here. But the idea is that you want to have some kind of order in which you've measured your qubits, which you've probably kind of predetermined. And then you want to find a way to push the pies around so that there's no errors caused on those already measured qubits, which is why here we push the pi onto the F, but we get errors on A and B, which we're saying we've already measured. And so we have to be able to then push those onto something that hasn't already been measured, like the outputs here. And it's kind of desirable that we can always push things onto outputs, but this isn't always the case, especially if we have a lot of internal spiders. But yeah, when we do focusing, a focus G-flow is essentially when we've pushed all of the green pies as far into the future as we can. So in a focus G-flow, we have that essentially XY measured vertices only obtain red pi corrections. And so it was explicitly we have that the only XY measured vertex to appear in an XY measured vertex's correction self is that vertex itself. Sorry, in its own odd neighborhood is that vertex itself. And so that essentially it means other XY vertices can only appear in correction sets. And this kind of corresponds to whenever we see a green pi, we just keep pushing it forwards onto outputs. And so, yeah, that's one way I've kind of thought about these things.
Thank you. I have another question, but just in case the audience have questions, if anyone have questions, you can jump in now. So my question is, when we look at, does anyone have questions? Sorry.
I had a question, but I'm not.
Sorry.
If Tommy can answer this, or maybe it's more of a question for Vinian, which is what Can you say a bit more about what the problem is about trying to extract circuits from diagrams with Pauli flow? Is that computationally difficult, or is it just that the circuits you get are not as good?
So I thought originally I was kind of sure that this would work with Pauli flow and that things would be nice. Essentially, what I think it is every application of neighbor unfusion that can be done with Pauli flow but not with gflow doesn't actually end up optimizing two-qubit gate count for whatever reason. So the way we kind of thought about this is we looked at Corbinian came for a research visit and we kind of tried to figure these things out, and we ended up looking at kind of paths through the diagram, and you can kind of think of information. It's easier with gflow, I guess, slightly less obvious with Pauli flow, but like the kind of how the information passes through the diagram, and you can kind of always get these specific lines of like, especially for like a focused flow, where a focused flow it cares about everything being correction sets, and so you kind of get this qubits in this qubits correction set, and then this qubit is in the previous one's correction set, and you kind of get this chain going from inputs to outputs. And it's essentially, if you apply neighbor unfusion along one of those chains, it works. But if you try and apply neighbor unfusion between two qubits that are on different chains, it doesn't preserve gflow. And it seems to be those try to apply it across the across two different chains of information flow, where this doesn't give you any optimization. There's also something to do with the Pauli flow extraction procedure is slower in general, but this is mainly because the finding Pauli flow algorithm is slower. And so I had talked about potentially just kind of finding a gflow at the start before you do any of these neighbor unfusions, because at first everything will be just XY measured vertices. So I don't know. Before we've introduced this X measured vertex, everything is arbitrary planar measurements. And so this thing, the diagram on the left, before we've done any neighbor unfusions, will have a gflow. And then I was thinking, okay, if we find a gflow there, track all of the changes to correction sets from applications of these rules, and you'd have a Pauli flow, and you can track how the Pauli flow changes, and then you wouldn't need to find the Pauli flow when applying the finding algorithm. But this just didn't get a speed up. Corbinian wasn't sure if it was his implementation of the Pauli flow extraction procedure, because I think he had some struggles with that because it works very differently to the gflow one. But I'm not 100% certain. Yeah, I think Miriam, Corbinian, and I are going to have a chat soon about what's happened since these things. And yeah, if I hear anything more, we'll let you know. Or obviously, you could, yeah, if Corbinian joins sometime.
Yeah, thanks.
No worries.
I also have a question if I can butt in.
Of course.
I was interested when you said like drawing like these paths. Is there any way in which you can see any of these flow conditions as like kind of making the edges in these graphs like directed or something, and trying to ask for cycles or something like that?
So I mean, in some way, so we're in Will Simmons' research, his paper on this stuff. It was all about Pauli DAGs, and that was all about finding directed acyclic graphs in the like the directed acyclic graph kind of encodes the time flow through the diagram in some way. But yeah, Pauli measurements get a bit weird when you talk about the DAGs, because they can appear in the past of things, but then still, yeah, like they can, you can interact with the Pauli measured vertex in the past, but it doesn't do anything to it. And so I think fully trying to formalize this with Pauli flow it could be a bit hard, though Will's done it with some kind of cheat somehow. But yeah, I haven't followed. It's been a while since I've looked at the DAG stuff. But yeah, if you're interested in the path stuff, I can try and find the example, the paper we were looking at that for mainly, and send it over to you. I think it's by Miyazaki.
Yeah, that'd be interesting.
Sure.
I have another question. I know Sarah wanted to ask a question, but she's being silent.
You go ahead. You go ahead. I'll ask after you.
So you have these like classes of flow preserving rewrites for different kinds of flow, I guess.
Mm-hmm.
Is there any kind of flow such that all of like the stabilizer ZX rewrite rules preserve it?
So not in particular. So a lot of the problem with stabilizer ZX rules is that they don't immediately preserve the MBQC form. So like spider fusion, this vertex splitting is essentially the spider unfusion for MBQC form diagrams. So we kind of need to look at flow preserving rules slightly differently because they need to preserve both flow and the structure of the diagram. And so, yeah, this does as much of spider fusion as we can really do here.
Okay.
Especially kind of going backwards is exactly just spider fusion. This is some kind of spider unfusion plus identity rule plus two color chain, like plus a Hadamard identity insertion. But yeah, we've looked at a lot of the stabilizer rules, and a lot of them kind of do preserve it. So like the bialgebra rule, if you rewrite it in a specific way so that you kind of just color change all red spiders to be green, and then everything has Hadamard edges between them. I believe the bialgebra rule preserves Pauli flow. I proved that at some point. I think you may also be able to. I think the bialgebra rule is actually a special case of a 2Z insertions in a pivot. Because bialgebra actually looks a lot like pivoting in a specific way. But yeah, a lot of the rules from the stabilizer ZX just don't really fit because of the way they're written out. Like
all of the rules that preserve flow are like kind of weird variations of the stabilizer ones. Like none of them come outside of stabilizers, right? Or
yeah. So
okay.
Exactly, they're all like a lot of them have kind of just been based on stabilizer rules that we like. The Z deletion is where is it? Z deletion. This is just pi copy, right? And the one of the strong complementarity rules essentially. And so yeah, a lot of my when I started out doing things, I was kind of looking at the stabilizer ZX rules, rewriting them into MBQC form as best as I can, and then trying to prove that preserved Pauli flow to some extent. And then yeah, I spent some time looking at the non-stabilizer rules, and then everything's just a mess because all of the extra rules you add on are just chaotic, and there's no real nice way of trying to write them in MBQC form, or it just seems kind of pointless.
Thanks.
No worries.
So I wonder, in 2023, Colin showed this flow preserving rewrite rules can be used in circuit optimization. And in 2019, Alex and Miriam had this paper on ZH calculus, which is for the Toffoli-Hadamard circuit. I wonder what would be the difficulty of using the flow preserving rewrite rules, or like generalize this rewrite rules to ZH calculus for the Toffoli-Hadamard circuit optimization.
So I haven't looked at this all too much myself. I believe Piotr in the comments may have spent some time looking at this. I believe it's really hard to define what a flow would even be in ZH. And so that's where the main kind of difficulty of all of this begins. It certainly would be very interesting to see, and I'd like to see that. But yeah, I've spent some time kind of towards the start of my PhD trying to think about flows in ZH, and I got nowhere. And so that seemed to be, it kind of fell at the first hurdle. But yeah, I think it may be possible in some degree. I don't know if Piotr has any comments. I believe he said he had thought about this, but yeah, I don't think that's like immediately feasible.
Yeah, so maybe I'll just quickly answer. So the problem is that correction, when we are working with ZH, it might require to change the measurement basis. So not just application of Pauli gates, it might require to switch the bases completely, like for example, between X and Z. And because of that, it seems to be very difficult to define flow.
Perfect. Yeah. Thank you for the comment. Yeah. Yeah, so I've not looked at that all too much myself, but very good to know. Does that help at all?
Yeah.
Perfect.
Thank you.
No worries. Thanks again, Piotr.